let's just look into the mountain car example, just to get a bit of understanding and sensing about how we can use neural networks or in general any model to just do the approximation. So you have seen the mountain car example, right? So it's in gymnasium. If you play around with the gymnasium, this is one of the examples. So how it works, you have this car in the valley, and then this guy could just accelerate to left or right or do nothing, right? So it's like you play the game, you have either left or right, or you have nothing to press, right? So these are the actions that you can do. So the action space, is still discrete, right? So we are not getting yet to the continuous actions. It needs a bit of time till we get there. So still we're thinking about discrete actions. So it's either left, right, or nothing. And the things that you can see here in this problem are the velocity and the location. Now, what you want to do, you want to get out of the valley. You want to get on top, right? And of course, you just probably you accelerate to left, you go up, you come down, and again you accelerate to right, and you keep on going this till you get out of the trap, right? Now, the point is that the car is going to get -1 each time that it's doing an unsuccessful trial. So at the end of the day, the car wants to get out of the valley with the least amount of actions, right? Now, here in this problem, the state of the car is actually where the car is, right? And then there are lots of things involved with the problem, right? All the dynamics that is involved with this process, like the location of the car, the speed of the car, the acceleration level, the friction with the surface, all of them are part of this stage, right? But you do not have access to all of it. What you see if you play with it, you see that you have only access to velocity and the location, right? Now, your state is somehow represented with these two parameters, right? No one can say that this is the complete state, right? I mean, of course, for the dummy game, this would be the complete state because the game has somehow designed with that, right? But in practice, this is not the only thing you need, right? So this is just a representation, first thing. Second thing, x and v, they are continuous, right? So if you want to think in terms of tabular reinforcement learning, how many states do we have? Like the capital N, we were always saying, okay, we have S1, S2, these are the possible states. How many of them we have? Yes? Go ahead. A lot of them, infinite, right? Yeah, because they are continuous, exactly, that's correct. So you pretty much have any continuous combination within the feasible region. This is what you can be there, right? Be in, right? So x and v, both of them are continuous, and then you have infinite number of possible cases, right? Now, if you want to solve this problem by tabular learning, reinforcement learning, what should you do? You need to quantize it, right? So you would say for example, x could be any number between a and b, right? And then I'm going to say, okay, I'm going to have x1, x2 till some x, I don't know, g, the grid points. And then the first one is a, the second one is a plus a q, the next one is a plus 2q, and you keep on going till you end up with b, right? So you grid the possible locations that you are in, right? Same thing for the velocity. You would say, okay, velocity is between some v0 and v1, and then I would have the same story, right? So I'm going to just break it down into v1 till vg, and then this is v0, v0 plus q, and so on till v0 plus, till v1, right? Okay, this was not a good notation. So say VB, VA. So here is VA and then VB, right? So you're going to agree. Now, Isa is going to solve it after the reading week for you with both quantization plus reinforcement learning, tabular reinforcement learning, and the version of deep reinforcement learning, which you have idea by then. But the key point is that if you want to think about the number of states that you have, well, in theory, you have infinite number of states. In practice, say you have G grid points here, G grid points here, you have G squared possible states, right? Every combination, right? Like X1 with V1, X1 with V2, all of the grid points, right? Then X2 with the first grid point, and so on, right? So you have G squared number of possible cases, right? So now, what we can do if we want to just give it into a neural network, we can essentially, or any model, we can essentially forget about quantization or anything, right? So we can say that, okay, V and X, both of them, are two parameters. They are within one feasible region. So I give these two. So this vector X of a state, V and X, this is my representation of a state, right? This is the feature representation of this state. And I give this V and X into the neural network, right? So V is going to get multiplied with a bunch of weights. X is going to get multiplied with a bunch of weights. They are going to add up, and then it might be more layers of processing. Finally, I'm going to end up with one value, which is the value, estimate of the value for this velocity and this location, right? So this guy is much easier to work with as compared to quantization, right? You don't need to make that giant table anymore, right? And if you need too much complexity, you just add the complexity to your neural network, right? So here the story is much simpler because in terms of representing this state, because you don't care about the fact that this guy has infinite number of cases. Your neural network is a function, right? So whatever your input is, it's going to give you some output, right? And as long as you make your output for specific points fine, then probably for the other points, the output is also fine, right? Okay, so now this is the way that we are going to approximate the value function. So if we want to just approximate one particular value function, then I am going to just give the representation of the state, and I give it to my neural network. That representation could be simply V and X, the velocity and the location of the agent. And then what I want at the output, I want an approximate of my value, right? For now, we're just talking about prediction, right? We are assuming that we have one policy, and we want to only evaluate how this policy works. We are using that neural network, okay? Now, what can I put as this model, as the model which is computing the value for me? Well, we can do linear approximation, right? We talked about this. And we're going to get back to this today again to show you that this is actually the case when you are doing the tabular reinforcement learning. But this could be a simple linear model, right? So whatever your representation is, every single guy is getting multiplied with its corresponding weights, and then it's going to go add up and give you the output, right? This is the simplest model you can think of, right? What are the parameters that you need to learn here? The weights, right? The weights that are getting multiplied with the features of this state, right? So, for example, in our mountain car example, we could have we have two different parameters. Then we have basically two different weights, and then you multiply those weights with these corresponding features. Then this is the value that you get, right? So what you are assuming, you're assuming the value of every single state represented by the velocity and the location is basically a linear combination of these two parameters, right? Now, what are those linear weights that I need to know? Well, I learn it from the samples that I collect, right? Everybody's clear, right? Now, considering this one and then looking at this case, okay? In this case, I told you we have G squared number of points, right? This means that, say for example, G, the number of grid points that we consider for velocity and location, each of them is 10. Then you're going to have 100 different quantized states, right? 10 for velocity, 10 for location. The pair are going to be 100, right? Now you have 100. If you consider the value table, how many entries do you have in that value table? 100, right? For every single quantized state, you have one value, right? And if you want to use tabular reinforcement learning, you need to learn all of these 100 values, right? And then this means that if for each of them you need 100 samples, then you need roughly around 10,000 samples, right? So you need 10,000 samples to rely on that one, whereas in this case, you have only 2 weights, right? Well, this can be learned with much less samples, right? I can just consider 2 different points, xv, x1, v1, x2, v2. I just try those 2 different points several times. I estimate the value of them. Then I try to find w1 and w2 that at those 2 points, it fits what I see, right? And then for the rest of it, well, I rely on that model, right? So this is the difference. But there is one obvious disadvantage here. And the disadvantage is that I am just training 2 weights, right? Whereas there I am somehow learning 100 parameters, right? And this means that this guy could be less reliable, correct? That's right, but can I improve it? Do I need really to rely on the tabular, or can I improve this one? I can improve that one. How can I do it? More layers, right? I just make the model more complicated, right? So I can, for instance, put one deep approximated, deep neural network, right? So I don't really need to look at xv and multiply it with weights and that's it, right? I can do multiple layers and I can just expand my hidden layers, right? I start from xv, then I go to one layer with 1,000 neurons, right? And then out of that, again, I do the processing on another layer with 1,000 neurons, right? And then at the output of that, I compute one single output. And that single output is my value, right? So I can eventually make it deeper and more complicated. And by doing it, I'm just increasing the weights that I have, right? And by increasing the number of weights, I am increasing the capacity of this model. This model is now able, maybe, to capture the true value function, whereas the previous one was not able, for example, right? Everybody's cool, right? You see this. So the key point here is that actually, in this case, we are having more degrees of freedom, right? Because we are able to just work with very tiny model, which has few weights, and then we can learn them with few samples. If we really have more samples, we can simply improve our prediction quality by increasing the size of model and doing better training on those larger number of samples. Whereas in the tabular case, I cannot do that, right? In tabular case, it's only about the samples. Like I get more samples, I can rely more on my estimates, right? And there are a bunch of points which I never see, and then I have 0 estimate for them, like totally unreliable estimate, right? So I can do deeper networks, and by that one I increase the weights that I have. For instance, here if I have 3 different neurons, then I'm going to have 9 different parameters, right? Each of them has its own weights and bias. Then I could have, say, 9 different weights. It's more than 2 weights which I had in the linear model, right? And then this guy is more capable of capturing the true value function as compared to a linear one, right?